All right. So Go plus WebAssembly. Let's get going. So what's the worst kind of bug? It's, well, one of the worst. It's when you get the bug that reveals itself once in a month in CI, but never locally on your laptop. There are many types of those bugs, maybe race conditions, maybe you have some dependency that's written in a unsafe language, like for example C or C++, and sometimes due to some undefined behavior it crashes if the stacks are aligned just right, and it's quite terrible. So now imagine if using some kind of seed you could reproduce this behavior of failure every time the same way and iterate on it to fix it, basically. So this is basically what the first part of the presentation will be. Later we'll be getting into using WASM from Go, but now we'll be talking about compiling Go to WASM. So, but before that, let's talk about, oh, it's not changing? Oh, nice change. Let's talk about distributed systems. So let's say we have a service and a database. And let's say that this database is sending a request to the service that's not idempotent. So if it sends this request twice, it will have a different effect. And let's say in this sample scenario, this request is stuck in a wormhole because a switch ate it, it's swallowed by router, it's gone, and it didn't get to the service actually. So as you do in distributed systems, the database retries and everything is fine. But then the request comes out of the wormhole and everything fails, your data is gone and everything is terrible. So I think we can agree that debugging distributed systems is preferable than sticking a fork into your eye, but not by much. So, and the thing to actually, I think one of the only ways to get your distributed systems to actually behave the way you want is by deterministic simulation testing. So this is the first part of the presentation. And so what can you achieve by deterministic simulation testing? So like I mentioned before, you can reproduce your bugs. The simulation of the, that's the part of the thing. You start with a seed, and your seed is basically all source of randomness in your simulation. It's a bit like fuzzing, but for your whole application and not just a smile library that's using some input and outputs. Basically, you can view it as fuzzing, but for your whole distributed system. So you generate a random seed, you inject it into your simulation, and basically this way you can replace scenarios of your whole distributed system and debug them until you basically get the behavior that you want and eliminate all bugs. So, but unfortunately, Go is not really a great language to do deterministic simulation testing. Initially, when I learned about deterministic simulation testing, I kind of ruled out Go to be used with this approach because, well, the scheduler introduces some randomness that's not controllable. Fun fact, actually, Go scheduler introduces randomness on purpose. Actually, Go is adding some randomness to the scheduler. So when you debug your program and run it multiple times, you can more easily spot race conditions. So they do it on purpose. And it's usually great for manual testing, but for our purposes, it's quite terrible. The OS threads are also scheduled in a non-deterministic way. Time is also changing every time you run the application. And there's also IORI randomness, which is different every time. Even RAM access has different timings. So there's a lot of things that we would need to control here. So I initially ruled this out for Go, basically. I thought to myself, okay, you can do deterministic simulation testing in Zig and Rust, maybe in C, but it's not really something for Go. But here comes WebAssembly, actually. So WebAssembly, you can think of browsers when you hear WebAssembly, But today we'll be reframing it in a kind of different way. So we'll be using it to actually gain portability, determinism for our execution, and isolation for our execution contexts. But what actually is WebAssembly? So you can think of it as a different architecture or a VM, virtual machine. And most languages these days actually have a target that supports WebAssembly as a architecture or destination host of the binary output. And this way, basically, you have this one bytecode. It's kind of like the JVM from Java, which allows you to compile once and run everywhere. And it's not just the browser. You also can run it on different WASM runtimes. A popular one is, for example, WASM time, which is written in Rust. It's one of the most performant ones. And of course, you can run in the browser as it was intended by WebAssembly. But I think it's important to notice here that the scope of WebAssembly is far wider than just running things in the browser. It's kind of a universal bytecode from my perspective, and that's how we will be treating it during this presentation. So, when it comes to actually deterministic simulation testing, usually this kind of approach is used by actually database developers because, well, with databases, you can't go the usual way how you develop software with shipping the first version, waiting for bug reports to come in, and then iterating on it until it's largely bug-free. If you do this with a database, you lose all your customers before you have something that's usable. So Polar Signals actually is a company that was developing a database in Go, and they encountered actually this issue, and they wanted to do deterministic simulation testing like other databases. So by the way, other databases that kind of pioneered the deterministic testing approaches, for example, FoundationDB. They started working on this around 2010, and then they were bought by Apple, and now it's open source, so you actually can look at the source code of FoundationDB. And another one that's written in Zig is Tiger Beetle, which is how I actually learned about deterministic simulation testing. But now back to Go. So this is how you build actually your program to WebAssembly. You sometimes need to adjust it to actually compile to that target. If you have any platform-specific code, it would need to be adjusted. But if you didn't do anything fancy, then there's a high chance that your program will just cross-compile to WebAssembly. By the way, so when I did demos of this presentation, I noticed that a lot of people don't know about those environment variables. So they're actually great, Go OS and Go Arch. This way, for example, if I wanted to cross-compile to AMD 64 Windows from my ARM64 laptop, I could just substitute this for Windows and AMD 64, and it will just cross-compile without installing any toolchains, anything at all. It will just cross-compile. I will get an exe, and I can send it to someone to run on Windows. So that's one nice thing about Go. And yeah, so this is how you cross-compile to WebAssembly actually. And basically, when we cross-compile to WebAssembly, we gain a lot of control because WebAssembly is actually single-threaded. So you gain the determinism that you gain back determinism that you lost through Go routines and Go scheduler. You also don't have to worry about the scheduling of OS threads. And if we compile with fake time, by the way, the Go playground uses this flag to actually start at the same time every time. So this is simulated time, something like sync test, but for your whole program. And then we just need to inject some kind of seed for the actual randomness to have some kind of source. And yeah, so this way actually Polar Signals, by introducing deterministic simulation testing, they found actually 3 data loss bugs and 2 data duplication bugs. Quite quickly, they just made the simulator, made a small system that was kind of a cluster and clients like talking to it, and they just run it for a while until the bugs basically popped out. So the thing about deterministic simulation testing is simulating your customers and the environment that will run your app in before it actually gets to your customers, so you find the bugs early. And I think it's quite an underutilized approach to actually testing things. And there are actually 2 ways you can build your Go program to WebAssembly. You can set Go as to JS, and this will output this browser-ready JS bundle. And you can also set this WASM P1 flag. P1 is because I think there will be also a P2, but I'm not sure if it's there yet. And this way you can compile to runtimes directly. This way you get actually just a WASM blob without any extra JS like here. And WASM time is, like I mentioned, a runtime for WASM that's written in Rust. WAS0 is another one that's actually written in Go, and we'll get back to it later actually. Here are the sources actually for what I mentioned. I actually recommend reading this paper from Foundation DB about deterministic simulation testing. And like I mentioned, Tiger Beetle. And there's also this nice GitHub repo that mentions a lot of nice approaches to deterministic simulation testing. So yeah. Now we'll be doing a quick demo actually. So let me quickly change the screen here. All right, I think I have to zoom out a bit. Not this way. All right, so actually this demo is inspired because a friend of mine invited me to the cinema a few days ago, and we'll be doing a deterministic simulation test of this software that's used, that could be theoretically used by cinemas for booking seats in their theaters. So to explain a bit more, so what we'll be doing here will be we have this setup, and this is also by the way running in a browser. And I compiled this node that's using a mocked HTTP client and server to basically simulate this kind of Kubernetes-like environment where we have a few nodes that communicate with each other and propagate some kind of consensus, let's say. I prepared the seed on beforehand. This is our only source of randomness in this deterministic simulation test. And let me tweak a few variables here to make it more demoable. It hangs for a while when you press run because WASM steals the JavaScript thread. All right, so here you can see the nodes, and this basically is the seats in the cinemas. And here we have different nodes. So this is basically a typical case of horizontal scaling. Recently, let's say there was a popular movie premiere and the cinemas had to scale up horizontally to handle off the load. And we have multiple nodes, and when some guest wants to book a seat, they basically access the system via one of the nodes, and later the node has to propagate the consensus to the other ones to actually prevent double booking or something like that. So this is quite a complex distributed system already. We have a few nodes, but I think this is fine for our purposes here for demonstrating the approach. And this is basically all running on a mocked HTTP layer with injected delays and drops of packets. So let me actually run this. And because the time is also mocked, we can simply speed it up. So when it's this brown color means that a guest logged into this node and added a seed to his cart. And when it's green, that means that the guest actually confirmed a checkout. And red means conflicts and they need to be resolved actually. When the node turns blue, that means it accepted that another node got the seed. Yeah, and actually, I purposefully left in a bug in this system to demonstrate why this kind of simulation testing is quite beneficial from my perspective. So basically, after this presentation, after this simulation is over, we can use this basically progress bar to get back in the simulation and look at our expected or unexpected basically process of the simulation. So let's wait a while for it to complete actually. As you can see, at the end, almost all seats got booked, except the few ones. Here we still need to wait for the consensus, and that's basically where it's at. I actually know that 11 won't be filled because I ran this simulation with this seed already. So this is basically where it's at. And yeah, so if we actually examine this more carefully, we'll notice that during this part, when we run for a bit, look at seed 4. So two guests actually added this seed to their cart. And in a sec, one of them will actually proceed to checkout. So notice that node number 2 actually completed checkout. A customer logged in here and completed checkout. And I think we can all agree that this means that basically the guest that booked the seat here should get the seat, and that will be the correct way to handle it. But actually, if we proceed with the simulation, then we'll notice actually that after the conflicts resolve, it's not what happens. Actually, the node that gets the seed and the guest that gets the seed is a different one, is from number 1. And that's because I purposefully left out any consensus algorithm here. The conflicts are basically resolved by looping over the nodes, and the one that gets the seed is the one with the highest lexical order. So what we need here is maybe Raft, maybe Paxos or something like that. I don't know, but
simple FIFO.
Perhaps, but there's also the question of trusting the time of the different nodes. So it's you can argue about it. What's the correct approach here? Because there's also the question of trusting the clock of the different node. But yeah, that would be one way to solve it. But and it's an interesting thing to discuss. But anyways, through running this actually in a simulation like this and running the actual code of the same node that will be deployed later to some kind of maybe Kubernetes cluster, maybe directly to servers, we can easily spot those issues. And later, when we correct the consensus algorithm to something else, we can simply take the same seed that we use here and replay this scenario until we're satisfied with the behavior of the whole cluster. So I think, and I think this is a really nice way to iterate over it. Otherwise, you would have to actually spin up a cluster like this, and you wouldn't even then get always the same behavior, because sometimes when you run those seeds, you will find some edge case, and if you do it with a real cluster, you could potentially not get the same network delays the second time you want to replay it, for example, and you'll get actually a different end result that we have here at the bottom. By the way, if I go back here a bit, then you can actually see here at the bottom, there's a log of all of the HTTP messages. This is the smoked HTTP layer. And all of the nodes here, like I said, are running in one process, and they are spawned through WebAssembly. So yeah, that's the thing. And by the way, this for the person that asked the most question at the end, I have the code of this demo on this pen drive, and I will give it to them who asked the most questions. So if someone is interested in it, then I can do that. And yeah, let's continue with the presentation. Now we'll shake things up a little, actually. Let me switch back to it.
What type of computer do you use? Never seen such one.
I will answer after the talks, not to distract people. So, oh, and here actually I have a screenshot of running this simulation with the same seed. And you can see that the output, I don't know if you remember, but the actually alignment here is the same of the seeds. And this varies a lot by network delays, retries of actually book requests. So the point is that it's fully deterministic, and you can easily retest your system this way. And the point of actually doing deterministic simulation testing is for a tester like this to run continuously on your CI 24 hours every day a week. And this way, you can run it, and then when it crashes, you can find a seed that crashed it, or led to some unexpected behavior if you use a lot of assertions in your code. And this way, I believe that it's one of the few ways to actually eliminate most of the bugs that you have in your software before actually shipping to paying customers. So, like I said, this in deterministic simulation testing, this should run always. And then when something fails, it reports it to you, and then you debug the seed that caused the failure. So that's the point of deterministic simulation testing. And that's how people who develop databases like Tiger Beetle or FoundationDB actually use this approach. So this demo ran for a limited amount of steps for demonstration purposes, and because otherwise I couldn't save each state and rewind it because I would run out of memory. But in a normal situation, when you actually run this in your CI, you don't need that. You can just run the simulation and then replay it from the seed. So that's that. But we'll be going even further and beyond with WebAssembly, because once you start treating WebAssembly as a control sandbox, you can also do it the other way around. So right now we compiled Go to WebAssembly, but we can actually compile whatever we want into WebAssembly and use that bridge in form of WebAssembly to actually import that code into Go. What do I mean by this? So, as you know, Go is similar to C. It was created by vaguely the same people that worked on C, and you can quite easily use C code from Go via CGo. I even have an example here. So this is a small snippet of actually some CGo, and it actually might be more tricky than you think, because this code has a leak. And generally speaking, if you import any kind of dependency that's written in a unsafe language, from my perspective, this always ends up as corrupting basically your safe Go runtime with some undefined behavior from C or C++, which is quite messy, and it's not as fun and basically straightforward as some people might tell you it is. So the truth is that even still, when you do all of the steps and ensure that your C code or another unsafe language that you use via CGo is safe and doesn't have any bugs, you still have to deal with the pain of actually using all of the different toolchains to actually compile your code. So let's say theoretically we're shipping a desktop application that's written in Go, and we're using some kind of dependency that's written in C or C++. So right now, the popular platforms are macOS AMD 64, macOS ARM 64, Windows AMD 64, Windows ARM 64. And if you would be nice, then it would be also quite pleasant to compile for Linux AMD 64 and Linux ARM 64. So you have to basically install 6 additional toolchains. So, and at this point, your toolchains install as long as your test suite runs in your CI. So it's quite a pain to deal with. And as I mentioned before, if you use vanilla Go, you just set the Go OS environment variable and it compiles, cross-compiles without any effort, basically. So here comes actually WebAssembly to a rescue. And there's even this interesting case study of Go SQLite. This is actually the project that motivated me to do this presentation because they're doing something quite interesting. So usually, so if someone is not familiar with SQLite, this is basically a in-process database that you can use for desktop or server applications, and it's baked by file storage. So at least by default. So you use it locally and not like Postgres when you connect to an external server. So, and usually they integrate with SQLite via Seago. But this project actually does something else. They compiled SQLite to WebAssembly and import that blob in runtime through WASM. This is a runtime for WebAssembly that's written in Go. And this way, you have to compile one WebAssembly artifact, and it works on all architectures. It's pure Go, so no dealing with other tool chains. And one additional interesting property of this is that all of your SQLite connections to the actual file are sandbox. So if, for example, you're developing some kind of application that exports or imports some custom format that inside uses a SQLite database. In that case, you might want to protect yourself some malicious attackers that want to exploit your app, and that's one of the ways to do it. Another interesting property is that, so Seago, when it calls to C, it has to wind up the stack and transform it into a C stack and then back into a Go stack. You don't have this here, so if you run multiple Go routines, this actually approach can be more performant depending on your workload. So it depends, but if you have a CPU-heavy workload and don't use a lot of Go routines, then this might be slower. But if you have a lot of Go routines, then benchmarks can determine that this can be sometimes faster. But actually, yeah, the slides change with a delay. But actually, importing this WebAssembly artifact at runtime is quite suboptimal in this case, because where would we actually like to use something like WASM? For example, if our app has some kind of plugin system and we want to dynamically import them in runtime, and we don't really want to import it in runtime when we use something like SQLite, that's a fixed known module, and we know what it is at compile time. So we don't really want to throw on the user the overhead of actually transforming the bytecode to actually native code. And this is actually where another project that actually spawned during between when I submitted that I want to do this presentation and now, so it's about a month old, called WASM to Go. And it's a transpiler that transpiles WebAssembly to native Go code, actually. And the way that it works, it doesn't produce actually readable code. It produces, well, if I had to compare it to something, it would be obfuscated code. But it's basically a one-to-one mapping from WebAssembly to Go. And this way, you actually lose the runtime overhead of executing it via a basically virtual machine, and you have native code, and you gain the safety of actually not having any unsafe languages in your end executable. So it's there's a trade-off because the compile times can be quite extended because of this, because you have to basically recompile SQLite every time you compile your final executable. But in reality, it will be usually cached. So actually, the project GoSQLite recently switched to this transpiler. It's not yet in release, but that was what they use in master. And I think a good testament to the reliability of this project is that the cross-compiled SQLite WASM binary that's transpiled to Go actually passes SQLite's whole test suite, which is famous for being quite sophisticated. So that's basically it when it comes to WebAssembly. So my main point here is that WebAssembly, from my perspective, is not about the web. It's about controlling your execution environment and controlling the dependencies you include with your code, and you gain safe and portable and isolated execution. And that's it from my side. Thank you very much.